Ladies and gentlemen, we're ready for our second last mechanism that's on our test. Oh no, you said second last. On Wednesday, I need 10 more minutes to do this one. It's an abbreviated version of the one we're going to do right now. Wednesday, you're going to do ROH plus TSCl plus pyridine gives ROTS plus pyridinium chloride. It will take less time than the one we're doing now. In fact, it starts off exactly the same. So the first 4 steps are going to be, or 3, I think. The first 3 are going to be Wednesdays. And then on the top one, we also have a 4th step. He's doing a lot of talking. Let's just get this thing going. Poor nucleophile. So you think, oh, it doesn't like attacking things. Look at sulfur, please, and answer this question. How many bonds does that sulfur have to more electronegative atoms? Reminder, C, S, and I are 2.5. O is 3.5. Cl is 3.0. So how many bonds does that sulfur have to more electronegative atoms? 4. That means the sulfur is incredibly positive. You don't have to activate anything here. Oxygen attacks. I got another question for you. Given a choice, do you break a sigma first or a pi? Pi, it's weaker. Good guideline is it's about 60% the strength of a sigma bond, so it'll break first. So you have made this species here. And I won't draw that H that's on a dash, you don't need it. We have a new bond to a sulfur that has an O- on the bottom and a Cl here and here. Resonate back, kick off Cl-. So we did 1 step, and this is 2nd step. Oh, might get some comments from the morning section here. Because the morning section, I switched the order of these 2 steps. Sorry, should have been all blue. And you made a Cl-, didn't you? Pyridine loves protons that are strong acids. This is a strong acid proton scavenger. Wow. Nah, that's misleading. Its role. I want to be very clear. It's not itself, it's not a strong acid at all. Role. Proton scavenger for strong acids. And we have an oxonium. What's the pKa of an oxonium? -3, isn't that strong? Yes, that means pyridine can react now. It couldn't before. Can pyridine take the H off the alcohol before we started? No. What's the pKa of an alcohol? 17. What's the pKa of an ammonium ion, which is the conjugate acid of an amine? No. No. The amine is 40. That's not the question. The question was, what's the pKa of the product when this thing has picked up a proton, which is called an ammonium ion? Crude approximation is 10. Yeah. I can have -3 go to 10. I cannot have 17 go to 10. It's wrong. 17 doesn't go towards 10. So while I'm saying now it's appropriate to use pyridine now, it was not appropriate to use it here. You can't switch this. You could have used it here, with this oxonium or here with this oxonium, you can switch the order of these last two steps, but you can't do the pyridine right away. I keep saying it over and over. You can't disobey the laws of pKa. They tell us what happens in what order. Okay, so we got this. We're almost finished, everybody. I know we're over time. I appreciate you staying. And we got our bond of sulfur with a pi and a Cl. And how do you get this Cl bond on a dash when the bond to the O used to be a wedge? I think I remember something about a certain reaction flipping a stereocenter, because we're going to do that right now. Backside attack, that's a nice general way to describe the certain reaction. That SM2 reaction or opening triangle, both had the backside attack flipping a stereocenter, right? Same story here. Chloride, backside attack. Whoa, that's making a pi, isn't it? SO2 looks like this. Right there. So I see SO2 happening, but what about the Cl? The second Cl. It's not attached here. It's a chloride ion here. See? It leaves. I do have a small problem with this, but in this course, really, I don't have any problem. Because it contradicts a question I asked earlier. Right here. I gave you a choice. Breaking first a sigma or a pi, which one do you choose? Pi. So I'm going to give you the truth, and then, because it's the first course out of two, I'm going to say we're doing baby steps. Okay, so the truth is this. The pi does break first. Oh, I got a nightmare scenario because I hit a button I shouldn't have. I need that one. Okay, you didn't even see that. The truth is that breaks first, and then the electrons in this lone pair come back. And don't copy this, please. Sorry, I should have said that earlier. That's the truth. Red first, blue second. You're not ready for first and second. So just kind of forget what I said about pi versus sigma this time, and just bust off the Cl minus, because you can visualize that giving what's shown on the page, right? SO2 is happening here, right? Pyridinium is this. And chloride is Cl minus. And you are done with this mechanism. And you also got this. Cl minus, yeah? And this gave what's that? Pyridinium. What's this? Chloride. I'm just having fun with my highlighter now. SO2. Right there. Okay. And unlike chapter 8, this is a reaction that is driven by entropy. Explain that. The principal driving force in this one is answered with one letter in English that's already on the page. It's right there. What's that letter? G means what state? Gas. What state is the most random state? Gas. Which reactions are most driven by entropy? Those that create gas. There's an entropy-driven reaction. It's the opposite of chapter 8, where we said when delta S is 0, delta G is roughly the same as delta H. You're going to say, no, this is what makes delta G drive the reaction. The delta S is huge. Anyway, we'll talk about that briefly Wednesday, and when we come back to this different reaction, but it's very similar. And you're going to find lots of good practice questions for me. Before we go, look at this morning's study guide document, page 1. Reminds you, Fall 21 Test 4 is your study guide. It tells you 2 questions to eliminate because they're bond dissociation energy questions, which you're not going to have on this test. It tells you which one. So page 1 of this morning's notes. And that's the end of that story.